Good morning. Hi students. In this video lecture on transform analysis of LTI systems, we will discuss about generalized linear phase systems. Some of these slides have been taken from the presentations of Dr. D. Richard Browntree from the SPIN lab. Okay, and then we will now start discussion about the linear phase systems. Recollect from the earlier classes we have discussed about, for example, we worked out the example of ideal low pass filter, which has, let's say, the magnitude response of 1 for minus omega c to plus omega c on this omega axis. This was the magnitude response that we expect, and for that we have worked out what would be the value for its response in the time domain. We got a sink-like function there, correct? And then that was we ended up with having a system which is non-causal and also infinite impulse response system. So that time, once you make it causal, we realized that it introduces a phase distortion, and then we studied about what are the acceptable phase distortions, and that time we discussed about linear phase delay, right? We discussed about the linear phase delay. Then let's say if your y of e power j omega is equal to e power j omega n subscript d into x of e power j omega, okay, which means the angle of this term of your system is equivalent to minus omega times nd. This is essentially a linear phase distortion has been introduced. So for that, if we had computed y of n, which has given us x of n minus nd. So if we had a linear phase distortion or a linear phase coming from the system, all it does is a delay of the system, and that way once you move from an ideal system to a practically realizable system, we said that linear phase delays are acceptable because all it does is in the time domain the sequence would just have a delay which can be compensated. So in this we further generalize it. Okay, so before that, a linear phase, what we have, the way we defined a system that results in a linear phase is a magnitude and a phase delay, right? So the phase delay, let's call it as theta of omega. For this is, for example, minus omega times c. Okay, c here in our earlier notation is nd, and there is one more term we are going to use, parameter that we are going to use is group delay. Okay, how this is defined as minus d theta of omega by d omega. So you take derivative of the phase delay theta of omega with respect to omega and take negative sign of it. So when we move from a strict linear phase to a generalized linear phase, these are essentially the systems which have constant group delay. So in place of minus omega c, j omega c here, you allow it to be having a constant as well. Instead of a strict positive value here, you move to a of e power amplitude of e power j omega, which can take either negative or positive. So this is the relaxation we do, which is acceptable, can be compensated with other additional filters. So these are, then if we make these changes, then this is the general form of generalized linear phase systems, okay, which is brief referred as GLP, and these are also referred to as affine phase systems. Okay, this is what we would be studying in this lecture. Okay, so here, for example, if you look at here, theta of omega for a strict linear phase system is minus c, and group delay is minus c times omega, group delay is c. Whereas this system a of e power j omega into this again, if you take that, theta of omega here is equal to minus c omega plus b, but the moment you compute the group delay, that's equivalent to c. So these are essentially constant group delay systems. Okay, yeah. Again, in the these GLP systems, what will be of interest to us are 4 standard classes. Once you start studying in more detail about filter design, that is where you come across these names: type 1, type 2, type 3, type 4 FIR systems. This is how we refer to them. So it's important you know them by their name as well. Pay attention here. What we are interested are causal systems, okay, which means their response starts from n equal to 0, and for n less than 0 their response is 0. They are finite impulse response systems. These are the 2 essential conditions here. Now when we say type 1 system, it has 2 properties. One is odd number of coefficients are there, and it is symmetric. Easy to understand this with an example here. For example, you take this, you take here n, and let me just remove this. Let me try it again. This is n. For example, if you start with 0, 1, 2, this is the small thing you could think of. Let's say you have 1, 2, 1. Okay. You could see number of coefficients are odd, okay, but they represent it by so you could see it if you write it, the z transform of this h of n, it would be the order of 2. So basically m plus so number of terms plus 1 would minus 1 would give you the order. So it's a second order system. For example, second order filter, and number of coefficients are 3. Number of coefficients here is 3, which is, if you call this by m, this is m plus 1 coefficients will be there, and this is symmetric. So the symmetry you should see will exist at m by 2 here. So it is symmetric about this point. If this is the case, and what you do now is compute h of e power j omega for this function. That's one example. Is okay. What I will do is I will take you through the derivation for type 1. As I mentioned, 3 more are there. You work it out yourself, and you have the answers anyway here. You work it out and cross check with the derivations here. Okay, let's go through this first. Right, h of e power j omega, dtft is h of n into e power j omega n. There are only m non-zero values from 0 to m. You expand that out, and now you know that for 0th term is same as the mth term. First term is same as m minus 1 term. Second term is same as m minus 2 term. So they exist in pairs, and there is only one isolated term which is there at m by 2. So that's essentially the coefficients are same for 0th and mth, first and m minus 1, and so on. So here what has been done while expanding here, you have taken, for example, h of 0, which is same as h of capital M, and you club the complex exponentials corresponding to them: e power minus j omega 0, e power minus j omega m. Similarly for h of 1, e power minus j omega 1, and e power minus j omega of m minus 1, and so on. Only isolated one having no couple with it is h of m by 2 into e power minus j omega m by 2. What's next? You take e power minus j omega 2 common across all terms, right? And then, for example, this would give you e power j omega m by 2 plus e power minus j omega m by 2, the standard way you simplify these things. So that would result in e power jx plus e power minus jx would give you 2 times cos x. So same thing here, e power j into 2 cos omega by 2, h of 0, and so on. Only the last term, once you have taken e power minus j omega by 2, m by 2 out, will be h of m by 2. Okay, this is the final expression in which this has been written. Pay attention here and compare it with the general form there. You have an amplitude term. This is your amplitude term that has been seen in the previous slide. Okay, go back in the video if you want to look it back again, and this corresponds to your phase here, right? So the phase value theta of omega here is equal to minus omega times m by 2. Okay, it's symmetric about the middle one, so 0 to m by 2, simply you have here omega k here. Okay, and also note that this is not strictly this one. For this you would get added up, multiplied with plus or minus 1 depending on whether the cosine is negative or positive, and this is nicely falling into that generalized linear phase system, right? You have a symmetric system, so you end up with a symmetric among sine and cosine, you end up with cosine, and these are the things, right? Hope these things are clear to you. So that's one simple example. We will come back to it a little later, again to the systems, but first let's quickly go through the rest of the three. Right, for the type 2, same as the first one, except that instead of odd number coefficients in h of n, you have even number of coefficients. So let's draw one signal here. So even number 0, 1, 2, 3. Okay, it's again symmetric, so one possibility is 1, 2, 2, 1, and this is an example possible h of n that you could think of, right? So where is the symmetry now? Symmetry is with respect to a non-integer value. Okay, shifting of non-integer values, in more details about it we will anyway come back to it more while discussing about the sampling part. Let's quickly go through how you simplify it. As you could see here, while you expand and try to compute h of e power j omega, okay, it's h of n into e power minus j omega n. You have perfect couples here, nobody is left single, right? So but anyway your symmetry is around 1 by 2, so that's why, yeah, is around a non-integer value, so you get here omega plus 1 by 2. This is a symmetric function, so still you end up with the cosine, and here e power minus j omega m by 2 is there. Again you could see here this is nicely falling into the a of e power j omega multiplied with a function, okay, that has a real value, and of course an amplitude. This is an amplitude function, not a magnitude function, because it could have minus 1 and plus 1 values. So please pause the video here, you try to work out and make your own derivation and cross check the results with the results given here. Now let's move on to the type 3 system. How is it different? This is again, the first two are symmetric and the next two are going to be anti-symmetric systems, right? And then third will be odd number of coefficients. By this time you could already guess that the fourth one would be even number of coefficients would give you the fourth system with anti-symmetric. Okay, let me again draw an example here how it looks like. So by the end of this lecture, just by looking at h of n, you should be able to say whether it would be which of these four it belongs, or it doesn't belong to any of these four. That you should be able to say, right? So 0, 1, 2, that's the smallest one I could think of, and let's say I have here 1, 0 and minus 1. This is the h of n. You could see here it's anti-symmetric about m by 2 value. The simplification you do it yourself and check it out. Rather I would spend the time in taking a look at here the final result. Notice here this is anti-symmetric, correct? Because of that h of so the value will be negative. Because of that the other counterpart will have a negative value compared to this, which would result in, while you are taking the ones which having same coefficient but with the negative sign, you end up with the taking common, you end up with a negative sign. So you have 2j sine of omega m by 2 term, m by 2 minus 1, and so forth, so on and so forth. So additionally there is a j here coming out, okay, unlike the first two systems. So this j means it's nothing but e power minus j omega pi by 2. So you have a phase of here, unlike the first two, omega m by 2 plus pi by minus omega m by 2 plus pi by 2. Okay, and then you have a sine function instead of cosine, because this is an antisymmetric negative sign and 2j sign, so this is a sine, and this is an amplitude function which could also get multiplied with plus or minus 1. So do the derivation for yourself, but these are the important points that are to be noted down. Okay, let's go to the next last type of that, type 4. Okay, as we have seen in the previous slide, this would be even number of coefficients will be there with antisymmetric thing. So let's draw one possible example. You have n here, you have even number of coefficients, which means order is odd, 0 1 2 3. okay, if this is 1 and minus 2, right, this would be 2 and minus 1. Okay, and it is symmetric about a non-integer n value, basically 1 by 2 it is there. So because of that you get here 1 by 2. okay, sine you get, and because here you will have since there is a negative value, the values are antisymmetric, here you get a negative value, so 2j sine, again this is what you get. So similar to the earlier one, except that now you have k plus 1 by 2 symmetry. Okay, right, so that's the 4 possible systems. Now let's spend some time, we will on understanding if there is any constraint that is getting implicitly imposed because of the way we are considering these 4 systems. Okay, so for this let's start with h of z expression. Okay, z transform of h of n is when you have only m number of terms, 0 to non-zero terms, 0 to m, h of n z power minus m. Let's make a study for the case symmetric cases. So you assume that your h of n is symmetric. Okay, h of n is symmetric, that's what you are considering here, this being symmetric function. So in that case what can we say? H of n is equal to h of m minus n. M terms are there, so for example whichever is there at 0, you have the same value, h of 0 equal to h of m, h of 1 equal to h of m minus 1, and so on and so forth. What will you do now is, you compute now, because of that this h of n can be replaced with h of m minus 1, that would give you this value. Next step is use change of variables. You change that, then you write it, you figure out z transform of which impulse function, okay, in the time domain would give you this. In other words, this is z transform of what, that's what you try to work it out after making a change of variable here. So you pause the video here, you work it out, and then you cross check your answer with the answer that we are going to now discuss. You do the change of variable and okay, this is what you end up with. H of z equal to z power minus m into h of z minus 1. Okay, to make further analysis of it, what shall we do is, let this z be one particular value of z naught. Let's consider its value at r z equal to minus 1. What is going to happen then? H of minus 1 is equal to minus 1, yeah, z power minus 1 whole power m, that is again 1, so that's z naught is 1, so minus 1 whole power m into h of minus 1. Okay, now so far what we imposed is the system being symmetry, that's all we imposed. Now what we'll do is, let's consider type 2 system. What would happen in type 2 system? Your number of coefficients are odd, but the m value is, number of coefficients are even and m value is odd. So when you have an odd value here, h of minus 1 is equal to minus of h of minus 1. So is this expression valid for any non-zero value of h of minus 1? This is like saying a equal to minus a, possible only when your a is equal to 0. That means from that you could say that h of minus 1 has to be 0. In other words, it should have a 0 at z equal to minus 1. Okay, so now with this we could say that yeah, this is a summary. We will discuss the rest a little later, but first pay attention here. For a type 2 system, it should have a 0 at z equal to minus 1. What's the implication of it? Well, z equal to minus 1, what does that mean? Z equal to, what can we say about value of z being minus 1? So z equal to minus 1, that means you are here, so that means omega equal to plus or minus pi. That's what you get, this real axis. Imaginary axis equal to minus 1 is here, so that means the magnitude of it at plus or minus pi is going to be 0, correct, because it is having a 0 there at z equal to minus 1. Because of that reason, what you can say for sure is it cannot be used as a high pass filter, and also it cannot be used as a band stop filter once its magnitude becomes 0. Okay, and on the contrary, when it comes to the type 1 filter, there is no such constraint imposed. So depending on the sequence that you have, nature of the sequence you could have zeros and poles anywhere. So that's the most versatile system. The most versatile system would be the type 1. With that you could design low pass filter, high pass filter, band pass filter and band stop filter as well. On the contrary, type 2, you could design only low pass filter and band pass filter and not high pass filter or band stop filter. Again, the first table we have already covered, type 1, 2, 3, 4. Both first two are symmetric, next two are anti-symmetric, and then the order of so the number of terms that you have are odd in type 1 and type 3, even in type 2 and type 4. Essentially you have symmetry, anti-symmetry, even, odd, so that is giving you all the 4 combinations here. Okay, now in the similar lines of what we did here, by imposing symmetry, anti-symmetry, odd, even, you should be able to, the exercise for you is to prove that a type 3 system will have zeros at z equal to plus or minus 1. That's your first exercise. We are almost half done with that, but you follow it, you work it out. It's in very similar lines of the way we solved it for this. Similarly, so if it is a type 2 system, it should have a 0 at z equal to minus 1. If it is a type 3 system, you can prove, and you should prove it, that's the first exercise for you, that it has zeros at plus or minus 1, which means omega equal to 0, this magnitude or that comes out of that filter will be 0, similarly at plus or minus pi as well. On the fourth, so when this happens, anyway, when it is z equal to minus 1, it rules out to be used as a similar to the type 2 plus 1. Once it has a 0 at minus 1, it cannot be used as high pass filter and band stop filter, and it is giving magnitude to be 0 at omega equal to 0 also. That means it cannot be a low pass filter also. So it can be used only when you want to specifically design a band pass filter and not any of the rest of the 3. Similarly, the last one, z equal to 1, what you could say here is, well, omega equals to 0, so it cannot be used as a low pass filter. Similarly, band stop filter, okay, it can be used only for high pass and band pass filter. Okay, and all of them have a group delay of m by 2. We have seen it already, and this m by 2 will be integer, of course, when your m is even, which is the k, or m plus 1 is odd, which is the case for type 1, and which is the case with type 1 and type 3 systems. So which is the case with type 1 and type 3 systems, but not an integer for type 2 and type 4. Hope you are clear. This is a key slide summarizing the entire stuff. Now let's solve some examples now. Okay, what I will do is I will solve one example for a type 1 filter, and then I'll give you an exercise for the type 2, 3, 4. You just need to follow the similar, in very similar lines you would be solving. But to cross check your algorithms and to cross check your results, I'll give you how the output looks like. This is the input given. This, in fact, we solved it in the class in very detailed in the previous classes, but anyway we will look at it again. Quick look at that. You, for example, compute h of z. Okay, there are 0 to 4 only, it has non-zero values, so 0 to 4. H of n is 1 here, so that's 1, and z power minus n. Okay, it's a geometric progression, 1 minus r to the power of n by 1 minus r, n equal to 5 here, since we are starting from 0. Then how do you simplify this? By the moment you see, so by the way, we are interested in h of e power j omega, so you compute that in terms of z replaced with the e power j omega. This is where you end up. And how do you simplify this? We have done a lot of problems similar to this. The moment you see 1 minus or 1 plus e power minus j omega, you take half of it common, okay, here as well as in the denominator, and then you will write it, you will get in terms of sines or cosines both in the numerator and denominator. So you take half minus j 2.5 omega, and here e power minus j 1 omega by 2. So this you are getting, so it's minus, right? So what you end up getting here is j and j in the numerator denominator would cancel out, e power minus j omega 2 sine 5 omega by 2 by sine omega by 2. Again, as we did the exercise in the class earlier, you should be able to draw this manually on pen and paper, using pen and paper without even requiring the MATLAB. So we worked it out exactly on how to plot it, to see first the zeros and then followed by the other stuff, where to calculate and other things, right? And then when both numerator and denominator is becoming 0, L'Hopital's rule and other things. So you try it, drawing it out again as a practice. Okay, you could pause the video here and do it and then compare it with the graph. This is what you would be getting for magnitude and phase. Okay, now in the rest of the expression, like 3 examples are exercises for you, where you have to derive these expressions of h of e power j omega, draw it using pen and paper, okay, and then you cross check your results there. For example, this is the exercise 3 for you. Type 2 system is here. How can you say that? This is an even symmetric, but these are number of coefficients 1, 2, 3, 4, 5, 6, and the number of coefficients are even. So work it out. I'll anyway give you the final answer. You cross check that. I will not give you the analytical expression, but get your analytical expression, draw it and compare it with this graph. This is what you should be getting. And then of course you are encouraged to code it in software like MATLAB and generate these results. All I would do here is just bring your attention to something happening here, is about the zeros of it. We have seen at z equal to minus 1, it has a 0, which means at plus or minus 5 this should become 0. That's one simple cross check that you could do. Of course it could have zeros at other points are also, depending on the kind of symmetric sequence that you have considered here, but it should have, irrespective of your sequence, a 0 at minus pi. And by the way, this is 0, okay, this is pi, this is minus pi, and yeah, this is 0 to pi on the right hand side of 0, and this is minus pi. Okay, and yeah, this is, you should be also able to draw the phase plot. Okay, that's the 3rd exercise for you. And next exercise, 4th exercise for you is type 3 FIR filter. Again, get the analytical expression, try it using pen and paper, encourage to do a MATLAB thing, and then you should be getting this result. Okay, if you recollect, it will have type 3 FIR filter, will have zeros at plus or minus 1. Plus 1 means it should be 0 at z equal to 0, omega equal to 0, and minus 1 means at minus pi and plus pi. There could be of course other zeros depending on the kind of function you have considered. The next exercise for you is antisymmetric and even sequence, right? Work it out, and this is what you would be getting. If you recollect, it has a 0, as in all, irrespective of the sequence you consider, it should have a 0 at omega equal to 0, right? because z equal to 1 is the 0 it has, which means at omega equal to 0 the magnitude should become 0. So this is how it looks like. Okay, with that we are done with the generalized linear phase systems. Hope you are able to follow this. If you have any questions, comments, concerns, okay, any suggestions, please you may mention them in the comment section of this YouTube video, and you could as well get them clarified in the conference call, Zoom conference call that we will be having sometime in the next week. Okay, thanks for watching. Okay, yeah, bye, take care.